Ladies and gentlemen, welcome back to the third video on motion, or rather uniform motion. And with it, we're going to now start problems involving projectile motion. All right, let's just look at some open files here. All right, so what you have here is the first question, which is talking about a baseball thrown with an initial velocity of 100 meters per second. Okay, so a baseball is thrown with an initial velocity of 100 meters per second. You all know what a baseball is. So it is thrown with this initial velocity 100 meters per second at an angle of 30 degrees above the horizontal. So this angle is 30 degrees. That's what we mean, as shown in figure below. So here is 30 degrees. I'm not sure why I didn't put it here, but this angle is 30 degrees. Now the question is, how far from the throwing point will the baseball attain its original level? How far from the throwing point will the baseball attain its original level? So how far is just a horizontal distance? How far from its throwing point will it attain its original level? So the original level is just this point, this level here. So it will be thrown from this point at this level, which is the horizontal level. It will be thrown all the way to go like that parabola until it drops to the same original level. So that's what we want. So we want how far from the throwing point will the baseball attain its original level. Okay. Now, one thing you should notice that from this original level, going back to the original level, the displacement in the y-axis will be 0. Why? Because the shortest distance between a particle which has just been thrown up and it's getting back to the same level, so that displacement will be 0 because it has gone up, going back to the same level, meaning that its displacement in the y-axis will be 0. Okay, displacement in the y-axis will be 0 because it has come back to the same starting level. Okay, so now we always take up as positive. So this is what has been done here. Taking up as positive, the y component of displacement should be 0. You see that? Taking up positive, the y component of displacement should be 0. Okay. Why? Because it's coming back to some point. So displacement will be 0. The y component, that's the shortest distance in the y component, will be 0. Okay. So y is equal to vit plus half ayt squared. Y is the 0 here, which you have as 0. Okay, that's the displacement in the vertical plane, or rather the vertical axis. Now VIY is just VI sin theta. We know that times time plus half AY is just G, which is minus G, which is negative gravity, T squared. So 0 is equal to, we can factor out T here. There's a T here, there's a T here. We can factor it out and put square brackets, and then say VI sin theta. VI sin theta remains inside there, minus half GT squared. So you can have two equations from here. You can have T equals 0 and T equals this whole expression here. So I have T equals 0 and 0 is equal to this whole expression. So as we have here, VI sin theta minus half GT equals 0. So now at T equals 0, this was just the displacement in the Y before it was even thrown up. That's the displacement here. This is time 0. This is the origin. So this is time equals 0. So displacement is 0 at t equals 0 here, and at that point here. displacement in the y axis will be 0. So otherwise, for us, what we're looking for is the final point, not the initial point. We're looking for what happens at this point. That's why we want to find how far from the throwing point will the ball attain its original level. It is only attaining its original level at this final point here. Okay, so now taking this equation and solving for time from here, we're going to have half gt equal to v I sine theta, and making it the subject of the formula, we're going to have 2vi sine theta over g as the time of flight. So now, if this is the time of flight, we're also going to have what next? T is equal to 2vi is just 100 sine theta. Theta is 30 degrees. That's why we have 2 times 100 sine theta, which is 30, over g, which is 9.81, which is giving a total time of 10.2 seconds. So this is why I'm saying that we can now, so this is the time of flight. So now using the time of flight, we can now find the range. We can now find the range, which is the horizontal distance for it to attain the same level. So now range, how do we find it? Range is the x distance in the x-axis, which is r, which is equal to vixt plus half axt squared. But a subscript x is 0. I've been repeating this over and over. A subscript x is 0. Hence we get r being equal to v subscript ix times time, being equal to vi cos theta times time. Okay, so v subscript ix times time. Now vix is just vi cos theta times time. This part becomes 0, and we're only remaining with this part, which is this. This part is becoming 0 because acceleration in the x-axis is 0, as ax is 0 there. So this times this, we're having vi cos theta, which is 100 cos 30 times time. Now the time is just 10.2 seconds, which is 10.2 there. And we're having the range as 883.3 meters. So this is 883.3 meters. So that is how far it goes. That's the horizontal range. Now we can also look at a stone. Yeah, this is another example of a stone which is thrown from the top of a building at an angle of 30 degrees to the horizontal. Yeah, now this person is standing on top of a building, throwing a stone at an angle of 30 degrees to the horizontal with an initial speed of 20 meters per second as shown below. So it is thrown with an initial speed of 20 meters per second. Now the height from which the stone is thrown is 45 meters. Alright, let's look at this. The height is 45 meters. Yeah, it is thrown from a height of 45 meters, as you can see. So this is our building. This is the height of the building from which it is thrown, 45 meters. And remember, in our calculations, we would be taking upwards as positive. So from the origin, we'll take up as positive, down negative. From the origin or here, we have the origin, we have the x-axis and the y-axis. So the positive x-axis is going that side, the positive y-axis is going that side, the negative y-axis is going downwards, the negative x-axis is going that side. So what is the speed? Yeah, what is the speed of the stone just before it strikes the ground? That's the part B. Part A is how long does it take the stone to reach the ground? So this stone has been projected from top of a building, then it has to go all the way down. So we're looking for how long does it take the stone to reach the ground. Okay, so we'll treat the problems independently, where we'll take the x components and the y components of motion independently. Then we solve for them separately to work out the problems. This is how we work out projectile motion. So how long does it take the stone to reach the ground? So now when you look at the tools you have, you use what you have to solve the question. We know that the displacement from the origin going downwards is 45 meters in the vertical axis. So in the vertical axis, the displacement has been given as 45 meters. But since it is down from the origin, when you look at the origin is on top of the building, but it is going downwards. But we've chosen up as positive. Okay. When you look at what is up from the origin, it's positive. Down from this origin is negative. That's what we're saying. So since this is 45 meters below, which is down from this origin, it means that this 45 will have a negative displacement. So we'll use this negative displacement to find the time. Now, as you can see, taking up positive, that's what we state first. Now, y is just this displacement, which is below the origin, which is down, right? So, taking up positive. Now, y is equal to VIYT plus half AYT squared. So now this y is just our negative 45 meters, the displacement. Why is it negative? Because it is going down. It is going down from the origin. If it was going up, if this 45 was up from the origin, we would have taken it as positive. But now it is down from the origin. That's why it is negative there. Okay. So now, what is VIY? VIY is just VI sine theta. Now our theta is 30. So it is VI sine 30 times time minus half GT squared. So minus half GT squared. This minus is coming from the fact that gravity always points downwards. And we have chosen up as positive. So we have chosen up as positive. You must know that. So this is VI sine 30 times t minus half GT squared. So this is minus 45. Now this VI is just 20 sine 30. This is initial velocity, which is 20 sine 30 times time minus half 9.81 t squared. Simplifying further, we're having this is going to 10t minus this, which is 4.9 t squared. We can rearrange these terms to make this jump to the left and this jump to the left so that we get this expression here. Now, this expression is just a quadratic equation which we can solve for time using the quadratic formula. So using the quadratic formula, we'll just say put in the values in the quadratic formula. We know that this part represents A, this represents B, this represents C. So we know the quadratic formula says T is equal to negative B plus or minus square root of B squared minus 4AC over 2A. That's the quadratic formula. So plugging in the values for A, B, and C in the quadratic formula, we're going to have this expression. And solving for T, we're going to get 4.21 seconds. That's what our time would be, 4.21 seconds. Now, this is the time of flight. Now, what is the speed of the stone just before it strikes the ground? So, we want to find the speed of this stone after this time. We want to find the speed of the stone after this amount of time. So, we're going to solve independently for the y component of velocity and for the x component of velocity. So, we'll start with the y component of velocity and then the x component of velocity. So after finding those components, we're going to find the magnitude of those two vectors so that we find the resultant vector and get the magnitude. Okay, we're going to find the resultant from which we'll find the magnitude, which is the speed. So v subscript fy is equal to viy plus a subscript yt. Now vfy is just equal to vi sine 30. This is the initial velocity in the y component, or the vertical component of velocity. So this is the vertical component of velocity in the y-axis, which is just vi sine 30. So vi sine 30 minus acceleration in the vertical plane or vertical axis is just gravity, which is minus 9.8. That's why it is having a minus here, minus 9.81. T is just 4.21. So vfy is just equal to 20 sine 30. V subscript I is 20. This is the initial velocity, 20 meters per second, sine 30 minus 9.81, and that, simplifying, we get minus 31.3 meters per second. So this is the final component of velocity in the y-axis. That's why it's v subscript fy, final component of velocity in the y-axis. So the negative is showing that it is going down. Remember, we chose up as positive, but we're having a minus here, meaning that it is going downwards. So the y component of velocity is going downwards. That's why it is having this negative. How about the x component of final velocity, which is vfx, which is just vfx equal to vix plus axt. But ax is 0 because the acceleration in the horizontal axis is always 0. So if ax is 0, this will become 0, and then we'll have vfx being equal to vix, which is v subscript fx being equal to vix. And we know vix is just vi cos theta, which is just 20 cos 30, which is 17.3 meters per second. So found the vectors in the x-axis and in the y-axis. Now, to get the velocity, we just have to find the magnitude of these two vectors, this vector and this vector, and then find the magnitude. So v is equal to square root of vfy squared plus vfx squared. This is how we find the magnitude when you have two components. So you have a component in the y-axis, you have a component in the x-axis. How do you find the magnitude of these two vectors? You just square them, add them, then find the square root. That's how we do it. So this is v is equal to, and yeah, this diagram is just showing you the vector directions in which these velocities are pointing. When you look at this 31.3, it is pointing downwards because we have a negative v. And when you look at this 17.3 meters per second, so this part here should be 17.3 meters per second. This vector pointing to the right. This one pointing to the right, it should be 17.3 meters per second. Let me just correct that. Yeah, otherwise we don't want to be confusing people. So yeah, let's do this. Okay, doing that, now we can do this. Wait a minute. Okay, so this is wow, what's going on? All right, yeah, like that. Okay, so this is 17.3. Yeah, this is 17.3 meters per second. As you can see, it is positive going to the right. It's positive going to the right, huh? Yeah, that's why it is. It's positive going to the right. So the resultant of this vector and this vector will just pass along that vector there. That will be the resultant of vectors. We've done vectors. Okay, so from here we can even formulate a triangle. We can make this triangle here. This is a triangle where we have this vector being equal to this vector going down there. So you can get a resultant which is this hypotenuse. The hypotenuse is the resultant. So you just have to get vfy squared plus vfx squared and find the square root of this. So square root of that minus 31.3 squared plus 17.3 squared, and you're getting 35.8 meters per second. That is our speed. That's the magnitude of this vector. That's the magnitude of this and this. That's how you do it. And yeah, you have 35.8 meters per second as the speed. All right, now let's look at another example for a stunt flyer moving at 15 meters per second. Okay, so this is a stunt flyer moving at 15 meters per second parallel to the flat ground. So this flyer or stunt flyer is moving parallel to this ground here. This is the ground, meaning that this vector, whatever velocity this is parallel to this ground. This vector for velocity is parallel to this ground. Okay, as shown in the figure there. Now, how large must the distance x from this point to this point be from plane to target? Okay, let me just read that again. How large must the distance x from plane to target be if a sack of flour released from the plane is to strike the target? So wants to strike this target from this point here. From this point here, want to strike this target. Okay, want to strike this target, which is a distance x from the point at which it was released. Okay, so how large must the distance x from the plane to the target be if a sack of flour released from the plane is to strike the target? So our goal is to strike this target. So we want to find this x, but we're lucky we have the height here. We have the height which is 100, right? So we use this height 100, but look at how far it is from the starting point. The starting point is this point here. So I mean from this point going up is positive, from this point going down is negative, from this point going right is positive, from this point going left is negative. That's what we're saying here. We've chosen up positive, right positive, up positive, right positive from the starting point. So since this 100 is below the starting point, the origin, it will have a negative displacement. It will have a negative displacement. So we're trying to find this distance x. So let's use the tools we have. We have the height, but it's a negative displacement. Okay, it's a negative displacement because it is below the origin. It is below, it is down from the origin. All right. Okay, I hope you're getting this thing. And solution, first find the time to reach the ground. Okay, as we did previously, we first found the time to reach the ground. So find the time to reach the ground, which is just for us to get the time, we use the tools we have. The tool we have is the height, which is the negative displacement. As you can see, I've put a minus here, minus 100, because it is below this origin. It is down. Okay, we've chosen up as positive, but this 100 is down. It is down from the origin, the starting point there. So y equals v subscript iyt plus half ayt squared. So our y is just this 100 is equal to viy is just 15 sine 30. Of course, the 15 sine 30 is coming from vi sine 30. So we'll say 15 sine 30 times time plus half ay is just minus 9.8 t squared. Okay, so we have minus 100 is equal to um, minus 100 is equal to this sorry this is 15 sine 0, not sine 30. This was a mistake. This is 15 sine 0. Why is the angle 0? The angle is 0 because when you look at our launching velocity is parallel to the ground. So two lines that are parallel, what's the angle between two lines that are parallel? The angle between two parallel lines is just 0 because this is parallel to the ground. That's why I have been assigned 0 here. The angle is 0 degrees. So this is 15 sine 0. This is 0. That's a correction. This is 0. So sine 0 is just 0. This is 0 here. And this times this is just 4.9. So this is 4.9 t squared. Minus 100 is equal to minus 4.9 t squared. We'll get that. So t is equal to square root of this expression. Square root of 100 over 4.9, which is equal to 4.51 seconds. So you get that as the time to reach the ground. So to reach the ground, you have that time. So now in this time, we can find the range using the same time. We can say x is equal to vixt plus half axt squared. The same equation of motion. Remember, the range is in the horizontal axis. That's why it's in x, x, x. Now, ax is 0. Acceleration in the x-axis is 0. So we're having here a 0 and substitute. And this way expression is becoming 0. But vix is just 15 cos 0. Yeah, 15 cos 0, cos 0 is 1. So this times this we're having 67.7 meters. So that's our horizontal range. 67.7 meters is our horizontal range. Wow, this is nice. Okay, now let's look at this extra question on projectile motion. Where we have a tennis player wins a match at Arthur Ashe Stadium and hits a ball into the stands at 30 meters per second. Okay, let me just read that again. A tennis player wins a match at Arthur Ashe Stadium. Okay, so after winning, this same player hits a ball into the stands where those people are sitting, the people watching the tennis, at 30 meters per second. Okay, so this ball is hit at 30 meters per second at an angle of 45 um, at an angle of 45 degrees above the horizontal. So it's 45 degrees above the horizontal. That's how far it is hit. 45 degrees above the horizontal. Now, on its way down, the ball is caught by a spectator. Okay, so it was hit at 45 degrees. Now, on its way down, the ball is caught by a spectator. Okay, I think reducing it like that will be easier to analyze. So on its way down, the ball is caught by a spectator rather, 10 meters above the point where the ball was hit. So this is a spectator sitting here. Let's just enlarge it. Let's do that. Yeah. So a spectator is 10 meters above here, as you can see. The distance from this point to this point is 10 meters. The ball was hit from this point at an angle of 45 degrees with a velocity of 30 meters per second. So the ball was hit and it was going up until this person caught the ball. So this is what this tennis player did. The tennis player won the match and hit the ball. Okay, the tennis player hit the ball up there to the spectators. All right. So this spectator caught the ball, but this spectator was sitting at a height of 10 meters. So these are benches, you see. These are benches where people sit. But this one was sitting at some height of 10 meters. So to start with, we're told to calculate the time it takes the tennis ball to reach the spectator. Okay, we use the tools we have again. Simple, just use what you have. You have a height here. Mean that the only thing you can work with is the only thing you can work with is the components of displacement in the y-axis. Okay, if we are given this horizontal range, we would have used the horizontal range. Okay, we would have used the horizontal range to find the time, but now we only have the vertical component here. So we use the vertical component of displacement to find the time. And when you look at the starting point from where it was hit, this point here, this point, the starting point, is treated as the origin, and we choose up as positive, going up positive, going down negative from this point, going right positive, going left negative. Okay, you have to choose the coordinate system as we have always been doing. Now, as I have said here, taking up positive. Okay, this is the symbol I've used. Plus positive, plus up, positive upwards. So taking plus, this arrow pointing up is just showing that I've taken up as positive, which is this thing in brackets, up positive. Now, from this starting point going up, everything is positive. Now, when you look at this level where this person is sitting, this person is up by 10 meters in the y-axis. This person is up by 10 meters vertically. So this displacement will be positive. This displacement of 10 meters will be positive. So this is a case where we're having a displacement which is positive. As you can see, y equals VIYT plus half AYT squared. So this y is positive is equals to VI sin theta. So VIY is just VI sin theta times time plus half AYT squared. Now AY is just minus GT squared. 10 is equal to VI is just 30 sine 45 the angle times time minus half 9.8 T squared. Simplifying these expressions, we're going to get this expression there. Making this cross to the left, this cross to the left, and this being where it is, we're going to have this expression being equal to 0. Now we can solve for this using the quadratic formula, which is this negative b plus or minus square root of b squared minus 4ac over 2a. This is a quadratic formula which is well known, and you know that if this is our quadratic equation, we're going to have this part as the a, this as the b, this as the c, and we're going to plug in this formula. So negative b, this one, which is this, plus or minus square root of b squared, this same thing squared, minus 4ac, like that, over 2a. Okay, now t is equal to 3.79 seconds, and t is equal to 0.54 seconds. Okay, so for this case, you find that you have two values of time, but this value for time, which is smaller, which is 0.54 seconds, this is the time while it was going up in the air, but with a height of 10 meters. You see, there's a height of 10 meters here, right? But this ball first started from here, went up. Okay, it went up, reached somewhere here, and then it started going down before it was caught. But at the point at which it was caught, it was also 10 meters below the ground, like that. Okay, and there was also this part which is 10 meters below, I mean above. Okay, so the first point at which it was 10 meters below the ground, it was on its way up. So this point at which it was first on its way up is the time where we're having the 0 point, this small time, which is 0.54 seconds. That's where we're having the 0.54 seconds. Okay, so on its first way up, at the point where it got to 10 meters below the ground, it was at a time of 0.54 seconds. As we have calculated 0.54 seconds. This time was its first point at which it was 10 meters below the ground. So this is the first point on its way up. So on its way up, it's just somewhere here. Obviously, it was 10 meters below the ground, and then it went further up, then started coming down until it reached again at a point which is 10 meters below the ground. Now, this second point is the larger time. The second point is the larger time, which is 3.79 seconds. So t is equal to 3.79 seconds is the one which we want. And let's see here what we have. We have two values of time. One is the time on its way up, when it was 10 meters above the ground. On its way up, 10 meters above the ground. And the longer time, which is this, is on its way down when it was 10 meters above the ground. On its way down, but 10 meters above the ground. So we take the longer time, which is t equals 3.79 seconds. So our time is 3.79 seconds is what we want. 3.79 seconds. Okay, good. Now, what are the magnitude and direction of the ball's velocity at impact? Now, we want the magnitude and direction of the ball's velocity at impact. Wow. Let's now see what we will have at impact. Okay, we already have the time, right, which is 3.79 seconds. So the only thing we have to now find is the components of velocity in the y-axis and in the x-axis. So this is what we're doing. The x component of velocity is constant. Of course, we know the x component of velocity is always maintained, which is vfx being equal to vix. Okay, the x component of velocity is always constant, which is vi cos theta, which is 30 cos 45, which is 21.2 meters per second. This value remains constant all the way in the ball's motion. Now, let's find the y component of velocity using the tools we have, of course. And we can either use this formula, which is vfy squared must be equal to vyi squared plus 2ay times y, or we can use vy final is equal to viy plus ayt, but I'll go for the simpler method here, which is vy final must be equal to viy initial plus ayt. So vfy must be equal to 30 sine 45, which is viy. This is just 30 sine 45 plus AY, which is just 9.8 times time, which is 3.79. So this is VFY, which is just minus 15.97. So this is minus 15.97 meters per second. So here there should be a meters per second. Yeah, I just have to put it. This is meters per second. Yeah, I know my handwriting because I'm using these things. So the softwares. So yeah, this is V subscript Fy must be equal to minus 15.9 meters per second. Now this negative is just showing that the y component of velocity is pointing downwards. Mean that the y component of velocity, or rather the final y component of velocity, is just pointing downwards. Okay, but the final y the final x component of velocity is positive. So since it is positive, it means that it is going to the right? So this is positive, it is going to the right. This is negative, it is going downwards. So we have that as our y component of final velocity. So we have both the tools we need. We have the final component in the x-axis, which is this, and the final component in the y-axis, which is that. So our only thing we're left to do is finding the magnitude, which is the speed at impact. So v subscript f is equal to square root of vfx squared plus vfy squared, which is equal to square root of 21.2 squared plus minus 15.93 squared. So it's just getting the magnitude from these two components. That's what we're saying. That's how we solve for this. That's how we solve it. We must find the magnitude of this same vector having the x component and the y component. So this is how we find the magnitude. You take vfx squared plus vfy squared. Then you get the square root of that. You get 26.52 meters per second. So after getting that as your speed at impact, now you can get the direction. Now on its way down, the vectors are looking like this. We have 21.2 meters per second, which is VFX, pointing to the right, as I said, and this minus 15.97 meters per second, it is pointing down. Now, this vector pointing down there is just the same as us taking it pointing down from this point pointing down. So if we make a triangle out of these two vectors, we'll find that you have this vector pointing to the right, which is the same 21.2, and another vector pointing down, which is minus 15.97 meters per second. Now using this and that, we can find this resultant, which is this resultant is just this speed here we found here. So this is the final speed at impact, 26.52, which is just this hypotenuse here. This is the hypotenuse, this is the adjacent, this is the opposite, but we want this angle. We want to find this angle, which will show us the direction at impact. So now to find this angle, we are going to use tan theta using SOHCAHTOA. You know SOHCAHTOA, where we know that tan theta is just equal to opposite over adjacent. So tan theta is equal to opposite over adjacent. Our opposite is just minus 15.97, this one. Our adjacent is this, which is just 21.2. Okay, means that theta is equal to tan inverse opposite over adjacent. Our opposite is minus 15.97 over 21.2. So yeah, this is a point. Yeah, let's just be explicit. So that's a point. Yeah, so this is 21.2. This is minus 15.97. Now, to find theta, you just have to say theta is equal to tan inverse this quantity, which is given minus 36.99 degrees. So this is minus 36.99 degrees. This is our direction. Or in words, you can say 36.99 degrees below the positive x-axis. Because when you look at this angle, it is below the positive axis. It is below. But angles are measured anti-clockwise like that. So it is this value, which is 36.99, or you can say 37 degrees below the positive x-axis. Then you have your direction and the question is done. Alright, so we're done with motion, and I'm sure you've had a good time listening to these videos. If you have any questions, you can follow me and ask why not clear. So for now, have a good time and enjoy your day.